in SOGAT, in those languages which were given as SOGATs, but then I said, then we discussed that we can only do derivable things in that setting. So today we see how to translate SOGATs into GATs. I just updated the course notes, so you can see some like system F omega is quite concise as a SOGAT, and then I gave lots of examples of translations, what you get if you translate things from SOGATs to GATs. So you can look at the first order logic and system F omega will became very, very long things. Okay, so we will discuss what this very long thing is. Okay, so SOGAT to GAT translation. Okay, and so the main idea is that in simply type lambda calculus, we have this operator TMN to TMB to TMARB, which use this second order function. And now we just want some systematic way to get rid of second order functions and turn them first order. So this new lambda should be first order, and what we do is we collect all the things that are on the left hand side of an arrow in an argument into a thing called context that you have seen before. So this lump will become a lump, it will become a lump where we obtain from a term of type B, we get a term of type ARB. And then the fact that, and then most of these terms will depend on some context, okay? And the fact that this argument has an extra A dependency will be recorded in this context, and I write with this triangle operator, okay? So this becomes this in the, this was in the SOGAT, and this is the same thing in the GAT, and now it's first order, there's just all this dependency here, okay? And let's see how we do the same thing with the beta rule. So in the SOGAT context, we said that if we have a log F, and then we apply it to some A, then just F, meta-theoretic application to A, right? So this F was a function, and the A was just a term of the input type, and then I could just apply this F to the A. So in this setting, what we will have is, if I do then the F is this thing, right? So it's a term which depends on one more free variables, that's how I read it, than gamma, okay? While the resulting, like this term, which is in gamma, it doesn't have this free variable A, and so this thing here should also just be of type B, right? Because this is the function applied to an A, then I should get something of type B. So for this, I need a new operation which lets me perform this, the thing corresponding to this meta-theoretic application. And this is called substitution, but to be clear, we call this instantiation. So this bracket operation is called instantiation, and it instantiates the gamma by just the same gamma which is already here, which I call ID, and then the last variable is instantiated by A, okay? So this bracket is called instantiation. And the thing that I can write inside the bracket, that's what we call a substitution, right? This is just the thing, and some people call the bracket also substitution, okay? And yeah, so in the more in the less abstract definitions of languages, lots of the time this bracket operator is defined by induction or by recursion on the syntax. So now it won't be recursion, it will be just one operator of a first order algebraic theory. Okay, so this is the main idea. So let's see. So first I show what we get for simply type lambda calculus, and then we discuss what this is and explain what the general translation is. Okay, so maybe shall we do this? Sorry, question? No. Okay. So maybe first I just write here the second order definition so that you can compare. So we have types and terms. Arrow into time. Okay, and then we had lambda. Okay, and theta. So what was theta? Was lambda. A and eta was that sum t is the same as lambda x d applied to x. Okay, so let's see the first order version of all of this. So first of all, we need to declare what these contexts, these gammas are. So we have a context, that's a new set. Okay, and we also have these things which we can write in the brackets, which is called substitution. Okay, and now we add some bureaucracy, useful bureaucracy. So these substitutions can be composed, okay, just like morphisms in edges in a graph. If we can go, if there is a substitution from delta to gamma and one from delta to delta, then we get a substitution from delta to gamma. This is exactly like function composition, but substitutions. This function composition is associative. So you see my variable naming scheme is what this is called the Simonyi convention or Hungarian convention, because the Charles Simonyi, who developed Word and Excel or was the manager of these at Microsoft, he insisted that in the name of each variable, the type of the variable should be there. So we have the same thing, right? Because this small gamma is a substitution into gamma. So it's always the codomain which appears. The small delta is into big delta. So we don't just put the name there, we separate it by an underscore, but we just do the lowercase version. Okay, then we also have this identity substitution that is needed to express that law. Okay, and then we have left identity and right identity. So what is this? That if I compose identity on the left of a substitution, it remains the same, and if I compose on the right, the also remains the same. And then we have the empty context. Okay, I denote it with a diamond. And then we have the empty substitution, which is a substitution from any gamma, this diamond. Okay, and moreover, this empty substitution is unique. So there's only one way to come up with such an empty substitution. I just put it here because this is like the first part, and the rest will come here. So I just call this empty eta law, which says that if I have any other substitution into the empty, then that sigma is the same as epsilon. Okay. So this was just bureaucracy. Now you can start listening again, because so what I wrote here had nothing to do with what I wrote here, right? So whenever I want a GOT from a SOGAT, I pay the price. And this is starting to pay the price. Okay. And now I look at, oh, there is tie here. Okay. So then there must be tie here as well. Okay. And because types are very, very simple, I just leave them. Okay. So types will just remain set. And there will be function. So that's not very interesting, but let's look at terms, because terms are the ones for which we have these dependencies. So now terms really change. So terms are not just tie-on set, but they are, first of all, they depend on the context, okay? Then they depend on the type, and then they give you a set, okay? And actually, for terms, I have lots of more things to do, because I need this instantiation operation for terms as well. So and now I'm, by the way, now I'm going line by line. So this is a translation where you just go through all the lines, if you finish, then you're done, okay? And now we are dealing, so we start dealing with terms here, and it was somewhere here, okay? So, so I have this instantiation operation. So if I have a term of type A in context gamma, which means that the term can have 3 variables in gamma. Okay, it doesn't mean that all the 3 variables of the term, I mean, all the variables in gamma are 3 in the term, but if there is a 3 variable in the term, it must be also in gamma. Okay, and then if I have a substitution which tells me how to explain the content of gamma from delta using delta, then I get the same term in delta. Okay, I get the substituted or instantiated term in delta. And look, so this gamma A delta gamma delta A, this kind of, so this is like this composition was, right? It's like function composition, because it's a weird that it's contravariant, right? So this goes from delta to gamma, so then this thing doesn't go from delta to gamma, but it goes from gamma to delta, right? But this is you should think about this as composition, okay? And this composition is compatible with this. Sorry, this composition is compatible with this composition and this identity. So I have 2 equations saying that if I have some small a, which is a term, and I substitute it with the composite substitution, then it's the same as doing first the one substitution and then the other. And I also have the law that if I substitute with identity, then it should be the identity. Okay. Okay, and now comes the part where I want to explain what this is. So this triangle, it has to do with terms, because in this language we have term variables. You can see that in this language we don't have type variables, we only have term variables. We know this because on the left-hand side of the arrow, only terms are here. So this is called the term variable. Okay, it's a bit confusing that this operation, which we call context extension, so it adds a term variable into the context. So it takes a context, then it should add the term variable into the context. So it might be something term here, but actually the only information that we need to know in the context about the term variable is its type. So it simply adds a type in the context. And this is source of confusion so this is not a type variable, even though it's a type in the context. This is a term variable which has this type, okay? And so now we have actually now it's the other for context. So there are 2 ways to form context, either empty context or triangle. So context is really a list of types, right? Either it's empty or it's a SNOC list of types, because we like to put types at the end. This is just convention. Okay. So now we want to write this comma. Okay. So we want to be able to express this equation. So we need this comma operation. It's about building substitutions. So this is what it looks like if we have a substitution from delta to gamma, and we have a term in delta of type A, then we have a substitution from delta gamma triangle A. Okay, so context is a list of types, and a substitution into a particular context is a list of terms, which is expressed by this comma operation. Okay, so it's a list of terms, and this other list, this list which is a substitution, is the cons constructor of this substitution is this comma, which takes a substitution into a smaller context and then adds a new term. And then note that this term is also in context delta. Okay, just like this substitution. So in the end, this is what expresses that everything that is in the codomain context is coming from delta, is expressed by terms in delta. Okay. Yeah, and now we can already write this thing here, right? So, for example, like a particular example of this is if we have ID which goes from sub gamma gamma, and then we have some A which is a Tn gamma A, then we can just do ID comma A, and then according to this rule, it will be sum from gamma to gamma A, right? Just extends it with one extra thing. Okay, so the next operation is the opposite of this. So just as we can extend things, so we can go from gamma to gamma triangle A, which needs information. We can also just forget information. So we can go always from gamma triangle A to gamma, where I just forget about the extra variable gamma, and we call this P for projection, first projection, or this is called weakening. Okay, so if we have a, what do we use this for? So if we have a, let's say we have a term B, which depends, no, we have a term B, which is in context gamma of type B, then we can instantiate this term with P, okay, and then we get a term which has one extra free variable. You can think about this as the same term as this B, but it like vacuously depends on this extra A, which doesn't give any information. Okay, so this is the weakened version of small b, which has an extra variable. Okay, and note that, for example, this P has two implicit arguments, the gamma and the A. So when I wrote this P here, whether it has type A or whatever, it depends on what the implicit arguments are, and I just use something. But if you want to do this, I mean, if you want to be very precise or cautious, then you always write the implicit arguments. For example, this one has three implicit arguments, the delta, gamma, and the A. Okay. So P is this first projection. So from a gamma triangle A, I can get out the gamma, but from a gamma triangle A, I can also get out an A. That's the second projection, which is called Q, because that's the next letter in the alphabet. So, and it is a term because I'm projecting out something which has type A, so it gives me a term. And yeah, okay, and right. And then I have a few equations saying how this this triangle and the comma and the P and the Q behave. So I have that the equation that if I do P, I project, I apply a projection, I have a projection, and then I compose it with something which goes into the bigger thing, then it's the same as the smaller thing. Okay. So what do I call this? Triangle beta 1. Then I have triangle beta 2, which says that if I do Q and gamma comma A, then I get back A. Okay, and then I also have triangle eta, which says that if I already have some gamma A, okay, gamma A is a substitution from delta to gamma triangle A, then I can take it apart and back together, right? So I can take out the first component using P composed with gamma A, and then I can project out the second one using Q, and this thing will be the same as gamma A. Okay, so this is an eta-like law. So actually, right? So actually all of these things here together would be summarized as saying that substitutions to gamma triangle A are the same as a smaller substitution into gamma together with a term delta A. So this isomorphism, this would be the concise version of putting all of these things together. Yes?
I'm getting confused by the triangle eta rule.
Yeah.
Is gamma A the name of one of your meta variables?
Using extreme Shimoni convention.
No, okay, that's fine.
If the codomain is gamma triangle A, I just use a two-letter name. There's no space between them.
Yeah, sure.
They are connected.
It's one token.
Yeah, it's one token. Blackboard. Yeah. Okay. Okay, so now I'm very happy because I reached this point in translating my SOGAT to GAT. Oh, I did this before, so actually I'm here, and now I only need to do the rest, but the rest is quite short. So the general rule of the translation is that you need to do lots of work for sorts, but then when you get to operations, it's only double than the previous one, and when you get to equation, it's exactly the same number of stuff. Okay, so let's see what the rest will be. Okay, so llama, well, for llama, I already said what we will get. Okay, but I write it again. So if I have a term which depends on an extra variable, then I get a term which has AROB. And then the second component for LUM is I have to say how instantiation interacts with LUM. Okay. But before saying that, let me just do application, okay, because that's simpler. So if I have the application is very simple. It will be exactly like that. I just put gammas everywhere. So in most of the cases, it's easy. You just put the gammas there and then you are happy, right? So this application, I just say this application works in any context. So the function and the argument, they can be in any context. They don't have to be in the empty context or something. They don't care about the context, and that's what the next rule expresses, which I call the substitution law for application. So if I have t applied to A, and then I substitute it, it's the same as t substituted and applying it is A substituted. Okay. So actually, this is like when people define substitution as a recursively on the syntax, then this is one of the definitional equalities or parts of the pattern matching definition of defining substitution. Okay, so it's not possible to do this kind of thing now because we are just defining an algebraic theory. We only have operations and equations. We don't have a way to do recursion on this. Okay. I mean, we could do it that way that, okay, actually, we only define the syntax and then and then after defining the syntax, and then we don't write all, we avoid this operation. And then after defining the syntax, by recursion, we define this operation. But why is it the case that we cannot do this? Why wouldn't this strategy work? And just for defining the syntax, okay? I mean, it wouldn't be very good because we wouldn't get an algebraic theory with models and stuff. We would only get a syntax and then some recursively defined operation on the syntax. So why cannot we do it for this theory? Well, it's written here. This is the issue. That you don't first define the syntax together with this equation. because this equation refers to the square bracket, right? So you kind of already need to have the square bracket before, while defining the data type or your syntax that you do. So this is, if you want this equation as a quotient in your syntax, then you need some kind of mutual definition, and that's not easy. So the easiest way, which is very, very beneficial, other reasons as well, is just do it this way. Okay, so let's see the similar for lambda. So if I have a lam b, okay, and then I substitute it, then it should be the same as lam of b substituted, right? So what's wrong with this?
We need to lift the gamma.
Yeah, so what's wrong with this? Let's analyze this a bit. So what's the type of B is written here? So B has type Tm gamma A B, okay? By small gamma, as it's just like this, it's a substitution from delta to gamma, okay? So, and because llama of B is a term in gamma of A rho B, so it completely makes sense to substitute llama of B with gamma, because then I just get the term in delta of type A rho B, right? But now I want to substitute B with gamma, so they don't match, because the gamma only gives me gamma much information. So actually here the naming convention is helpful, but I know that B depends on both gamma and A, right? So yeah, the better naming convention for B would be something like B gamma A or something like this, where not only the codomain but the domain would be visible, and then it could be immediately. Okay, but we don't want to go that far. Okay. So what is the, so gamma is not good here, right? So what's the type of the substitution that we need to write here? Okay, from where and to where does it go? Can you calculate it?
From delta to gamma triangle A.
So it certainly goes to gamma triangle A, right? But does it go from delta? Let's see where it comes from. Okay. So maybe let me draw derivation rules, because here it's helpful. Okay. So on the here I want to write lam of B of something, right? And it needs to have type, right? What's the type? We already calculated the type of this. The right hand side must have the same type, right? Yeah, delta E rho B. That's what we want, right? Now the outermost thing is a lam, okay? So by the rule for lam, we know that this B something has to have type Tm delta triangle A B, okay? Okay, and now we can just look at the substitutions, okay? So first of all, we need to know that B has type Tm gamma A, and then the substitution which is in question now needs to go from here, right, to here. So that's the information which is encoded by the fact that this is the same as this, and this is the same as this, right? But now it's horizontal line notation, okay? So we hope, I promise you that I introduced everything that we need, so we should have enough little operations that we can put together to get from a gamma, which is just a sub delta gamma, to this. So yeah,
The type of B should be Tm gamma A B.
yeah, thanks. Yeah, okay. So how do we go from here to here? Okay. So let's just continue the derivation tree, because here is the rule how to go from into a triangle, right? Gamma triangle A. So let's just use that. Okay. So here we will write a comma. Okay, we decided. So the first thing in the comma needs to be a sub in delta A to gamma, and And the next one needs to be a TM delta A. So maybe let's do the TM first because that's easier. What's that? Q. Yeah, very good. Right? It's just this Q where the gamma is now a delta. Okay. So how do we go from delta triangulate gamma? So remember small gamma, I erased it, but small gamma goes from delta to gamma. That's our input. Okay. So, but like if you just think about it from a distance, like if I know how to go from delta to gamma, then I should also be able to go from something bigger into gamma, right? Here I have an extra, okay? But now I need to express the fact that somehow I forget that extra, okay? So what can I use for forgetting? Yeah, so P forgets it. So I have P, which goes from sub delta A to delta, okay? And I think I wrote them in the correct order because if I first do P and then I compose with gamma, then I will get something from here to gamma, right? So here, this one is just gamma compose P, okay? So I don't have space here, but this thing should go up here, and then that's the rule for composition. Okay, so now I figured out how to write the substitution rule, and I mean this is quite common, this kind of operation. So we could even define an operation which is called gamma lifting, which does this. So what this operation does is just adds an extra variable both in the domain and codomain of the context, which the substitution doesn't touch. It's like ID, but on this side of the context, on this side of the context, right? So this here, this ID, it didn't touch the first part and did something at the end. Now we have kind of the opposite, where we do something in the beginning, whatever that small gamma does, and then we don't touch the end, okay? And actually, there are lots of different ways to express this calculus. So it's in a way a matter of taste, which operations you add here and how do you do it. For example, you could express all of these operations, P and the Q, instead of some of these operations, you could have upper as a primitive operation, and then use some tricks to express the other operations and equations and stuff. But this is fairly standard, and so the name of this is or something like this is what is called category with families. With family, actually, I think that's the correct name. Category with family, and this is a simple version of category with family, because actually we did some cheating. We didn't do the most general translation because I said that, well, type just stay the same, because I see here that there is no operator which is a binder for types. Okay, but if we have for all or I or something dependent, then this very simple version doesn't suffice, and then I need types to also depend on context. But I mean, this is a bit simpler, so that's why we started with this thing. Okay, and then I mean, sorry, we still haven't finished. Sorry, because we still need to translate the last two rules. Okay, so let's translate them. Okay, we translated one of them already. So the beta law is lambda P applied to A is the same as T, ID, comma A. It's just that now we can, or let's call it B, just as above, B, right? Here was long B, and we already know that B is in this context. So, and A is in the context gamma. So here we need a substitution from gamma to gamma triangle A, and that's exactly what we get here. Okay, so let's express. So, and then compare it with this thing. It looks very similar. The meta theoretic application became an instantiation with the identity substitution and then adding this at the end. So how do we do eta? So for eta, we start with a term, which is Tm gamma A r rho P. Okay? And now we want to say that T is equal to some lambda. Okay, let's start writing lambda here. Okay. So what could this be? Lambda of what? Maybe let's also write derivation rules here. So I want lambda of something which is a Tm gamma A r. Okay, and by lambda, because I'm applying lambda, I need to write something which is in this bracket, which is a Tm gamma A B. Okay, and I have this T. So how can I from this T, if we just look at formally, this T goes from A to B, and now I want a term of type B in a context where there's an extra A variable.
Yeah. Maybe T dot something with Q applied to the Q that you can.
Yeah, that's a very good idea.
Oh, but so, the T itself might have to be lifted into the new with the triangle.
Yeah. So okay. So first of all, yeah, very good. Let's do an application. That was an idea, right? So one way we can decide it is that here there's an application, so we must use the application. Okay. But actually, because we have a function into B, we must be able to do application here, and even better, because there's an A in the context, we can just get an A, which is the input of a function. So if we have some function, now let's see if we have a function in the same context as this one, right? When we write application, it has, where is it? When we write application, it has to be the function and the input has to be in the same context. So this will be the function. So first of all, here, so here I will write an application of something to something. The first something is this, and then the second something is a term in, again, the same context, which is the input. Okay, and then let's start again with this input, right? It's just Q. Okay, so Q, so the another name of Q is the zero defined index, right? So, like, you could also say that we have V0, it is Q. Okay, what is V1? Maybe I write the type here. So this is Tm gamma A. So V1 should be a Tm gamma AB A, right? So we count from backwards. This is the zero variable and this is the one variable. How do I express it with this? This is called the substitution calculus part of the theory. Okay, so whenever I translate SOGAT to GAT, first I need to come up with, use some kind of substitution calculus. This is my substitution calculus, and then I get the rule specific to my particular SOGAT. Okay, the substitution calculus is based on D prime indices from 0, 1, 2. That's how everyone knows D prime indices. That's how I formulate them. The only catch is that these are well-typed D prime indices. Okay, so this Q has the gamma and an A as parameter. It's not just the number 0. It's much more information because the typing is also there. Okay, so what's the idea for V1?
I'm suddenly not sure anymore, but I think it's something with Q, and then between substitution brackets, the combination of P comma Q.
Okay.
Yeah, like I said, I'm not sure anymore.
So this is Q. Okay. This is Q, and then it's a very good idea that if we substitute Q with something, we end up here, okay? So, see, what is a substitution that goes from here to here, right? We need a substitution into this direction, right? So this is, in general, right, if I have a, what is it? If I have a T, which is Tm gamma A, and then I have a substitution into gamma, which is called small gamma, then I get T gamma, small gamma, and then it will be a Tm that value. So you can, like geometrically or like visually, you think this has to go inside, okay? And this is exactly what I need to do, right? From here to here, what's the substitution which goes from here to here? Yeah, it's just P. It only forgets the B, right? It's a simple P. So indeed, this is just P. I mean, and then V2. Okay, what is V2? Okay, continues here. V2. Again, I just add an extra variable at the end. So it's just QP and then another. Okay. Actually, by this rule, I have the freedom to do it this way. Right? But so here there's other, so think about this. So this one has to, V0 was a D prime index which had two implicit arguments, the context and the A. How many implicit arguments does V2 has? Now, if you wanted to define V2 as a separate operation, right? I don't know, it has quite a lot, right? Gamma, A, B, C. Because it has its own, like has the base context gamma, then the type A, and then you need to know about all the types which come after that in the context. Okay. So you could also define a you could also use a substitution calculus where you have concatenation of context. So here the context is really just a list of variables, and we don't have an operation which takes one context and concatenates another at the end. But if we had such an operation, then we could get away with fewer implicit arguments, because then we would have something like Vn, it would be like gamma, then an A, and then plus some delta, and delta would have, maybe I should call this V gamma A delta, right? Where delta can be empty, and then this would be 0, and if delta has like n, then it's the nth D prime index. Right, and this would have type A. Yeah. So, for example, if you want this, then you have two options. You either change your substitution calculus and add this plus as an operation there, and then you have a different class of models where your context don't only need to feature the triangle, but they also need to feature the plus. Or you just say that I don't care, I stay with the same class of models, same theory, but for the syntax, you can just define plus by recursion, okay? By the induction principle or iteration principle on the syntax, you can define operations on context, right? It's like, contexts are quite easy because they don't include any equations. So basically, for context, you can define operations by pattern matching. You say what it is for the empty context, you say what it is for the extended context. So the usual definition of plus on at least for functional programming, you can do things on the context this way, okay? But what you are doing in the background is using the iteration principle of the syntax or initial model of this algebraic theory. Okay. Okay. All right. So, okay, this was just a detour for D prime indices. So this Q was indeed the 0 D prime index. Okay, and now we need to write the function which has type AROB, and it's not in the context gamma, but gamma triangle A. So we just take our function T and weaken it, right? We have this, okay? So we know how to express, and so this is TP, this is Q. Now what to write here? We derive what we wanted to write here. So this is ln of P dot Q. Okay, so this is indeed the first order definition of simplified lambda calculus. Yeah, so this so now this is a car. This has a class of models and morphisms within the models and everything else that we already know how to do for God. It has a syntax, and for example, by induction on the syntax, we can prove normalization for this theory with a very similar argument to how we did it for simply type combinator calculus. Okay, it's slightly more involved because there you remember maybe we defined the logical predicate for every type, and then we had also to define re-phi operation mutually with the logical predicate. Now this theory has more equations than combinator calculus. For example, it has eta, while there was no eta-like thing in combinator calculus. So we expect that the normalization needs to be a bit more complicated. And it is because it's not enough to have e-phi, there's also reflect, which goes exactly the opposite direction. So when you do normalization, you need to say that if the logical predicate holds for a term, then it is in normal form. And in the other way, we also need that if something is a neutral term, which is some subset of normal forms, then the logical predicate holds for it. So yeah, so it's a bit more complicated argument, but you can do it on this theory, and it's a bit right. It's a bit more difficult because you have to, when you define a dependent model, you need to give cases to all of these things now. Okay. So we could have defined the simply type lambda calculus as this GOT in the first place. So why do you think it made sense to first talk about SOGATs and then the GOT version? Why didn't I just say, oh, you want to learn about simply type lambda calculus? Well, this is simply type lambda calculus. If you do enough exercises with De Bruijn combinators and everything, you will be able to use it after a while, right? We quite quickly figured out how to write down this rule, and we can do programming like what is the identity function? Okay, so let's write a function which has this type. We assume some type A. How do you write this function? So there's only one solution up to equality.
Lam Q.
Yeah, it's just lam Q. If I also write the implicit arguments, well, the first implicit argument of lam is the empty context, because that's what I want in the end. The domain is A, the codomain is A, and then the term the explicit argument is just Q, and the implicit arguments of Q are empty context and A. Okay, so this is the fully annotated term. Okay, and then okay, so we can already do functional programming here. Once you define the identity function, you can define anything. And let's just prove that even, let's say we have a term in now context gamma of type A, okay? In any context gamma. And I want to apply this A to my function. How can I do it? Okay, so let's call this IDF. This is the IDF. I have an A, and I want to write IDF applied to A. And I want to compute that it should give back A, okay? There's a mistake on the blackboard. Yeah?
I think IDF should be converted to the correct context being gamma. So you use epsilon.
Exactly. So this doesn't make any sense because like this kind of thing made sense in the second order description, right? Where weakening is implicit here, right? So just think about it this when you read this, the T is in some certain context here, but when I write T here, it has access to an extra pre-variable. So here Agda takes care of the fact that T has to be weakened to make sense. Now I need to do these things by hand. So now you see this is really a lower level language. It's lower level because I have to use De Bruijn indices instead of variables, but also because of these explicit weakenings, okay? So this doesn't make any sense. So what I can do is I need to substitute IDF with something to make it into context, turn it into context gamma. What should I substitute it with? Yes. So epsilon is very good. It takes me from anywhere into the empty context, right? It's the ultimate weakening, which weakens from into the empty from anywhere. Okay. And okay, and now I can apply it to it. Okay, so let's calculate it. So I have now I don't write the implicit stuff. I mean, if you do this kind of CWF algebra or substitution calculus algebra, what we are doing, I mean, just as you can learn how to compute with addition and multiplication, you can also learn to compute with this. Here, the thing is there are lots and lots of implicit arguments, and sometimes you make a mistake, and it's because you forgot to fill in or check some implicit arguments. So it's always useful to make Agda do this for you or something. Okay. But now we try to write it without implicit arguments. Okay. And also there are extreme, just as this is a sport, CWF, so there are extreme versions of this sport, like, there's marathon, but you can also run 200 kilometers and stuff like that. So there's, for example, Thierry Cocon writes this like this. So he writes this, QS.A. And yeah, you know what this is, right? His argument is, for example, that it's very nice that you don't write a square bracket and the composition, because then if you write A gamma delta, you know that its two sides are the same. So it's a good notation that there's no two separate ways to write the same thing, which is good, right? Okay, but I mean, okay, here we are trying to be pedagogical, so we do the poor man's version of CWF algebra. Okay. Okay, so now I can use the beta rule, right? No, I can't. Because the term that I have doesn't have this shape. What should I do? So, I mean, okay, let's write some more brackets, okay, to be clear what's happening. Oh yeah, there's already a bracket. I just put one more bracket here to make it. So it's indeed, this is an application term, but it's not applied to a lambda term, but to a substituted term. So somehow I started in the wrong context. Yeah. So okay, this was a good idea. So what should I do?
Maybe the rule about lambda instantiation.
Yeah. So the lambda substitution rule. With the help of that, I can push inside the substitution, and then I hope when I push it inside, it won't ruin my nice Q there. Okay. So here, so this was just definition. Here I use the lambda instantiation rule to say that this is, let's see, lambda Q something, and then the dot A remains. So what is the something? When I have an epsilon here, it becomes epsilon compose P, comma Q. Okay. So this is epsilon compose P, comma Q. Okay. So actually now I have multiple options. I mean, if I'm an interpreter of a functional language, then I just apply the function, right? But because we don't like to reduce under a lambda, but here when we do algebra, we can do either. So we could just simplify this thing, right? Because like this is a Q, and then we substitute it with a comma, right? And we had a rule for this. If the Q is substituted by a comma, so 0 de Bruijn index is substituted by something, then we just read out the last variable. Okay. So by the triangle eta 2 rule, okay. So by the way, I call these beta and eta rules so that this isomorphism is really like one direction is P and Q, the other is comma, and then the one direction is the beta rules, the other is the eta rules, okay? So with that, I just read out the Q, okay? So I have lambda Q applied to A, okay? And so also know that so this Q changed. The implicit arguments are probably very different of this Q and this Q. One of them is in the empty context, the other is in some gamma context, so that changed. So these all might be very different Qs. Okay, let's go on. Right. Okay. So now I should be able to apply the arrow beta rule. Okay, because we have multiple beta rules, it's good to decorate the name of the beta rule with which type former it corresponds to. So that will say that I need to write the body of the lambda, okay, and then id, comma, the argument, okay. Yeah. Okay, and then finally I can use the triangle beta 2 again to get the desired name, right? So, yeah. So, it's nice to compare this with what we had to do when we worked with the SOGAT representation, where we were also able to define IDF. When we defined IDF for the SOGAT, we didn't have to talk about which context it is in. And then when we did this reasoning, we didn't have to care about the lambda substitution rule, right? Because the substitutions were taken care by this second order syntax, the function space of the method here. We didn't have to care about this, and we didn't have to care about this, right? So, yeah, okay. Okay, so my question was, why is it better to, what do you think, why is it better to define simply type lambda calculus like this rather than like this?
Write programs, so get representation.
Yeah. Okay, but then maybe if I want not, I don't want to just write programs. I also want to do induction to normalization, for example. Yeah, so I mean, yeah, so that's clear that the GOT version is nicer because I have a notion of morphism. So that's an argument for starting already with this presentation, right? I mean, but this the answer is very simple. So if I start with this abstract one, and then I can turn a handle and get the dot, right? So there's an algorithm for doing this, and the algorithm also makes it sure that I don't mess up things. So maybe I write, what if I do it this way, then I write the wrong substitution, or I forget something. So this gives me some kind of guarantee that all the operations that I run in my first order calculus will have a substitution, for example. Okay, or in another way, so if you start with something like this and then you start writing down operations, then you have to do some hard work that, for example, your calculus is structural, or that that substitutions don't get stuck. Whenever you have a term, you can always push the substitution down, and then it becomes a variable. Okay. So if it's generated by these rules, then this is made sure by the system. If you do it for yourself, then you have to prove this by hand. So this is similar to defining a programming language as I don't know, list of lexical elements, and then you have to prove that alpha renaming preserves matching brackets, the famous matching bracket theorem. Oh. Have you ever seen the matching bracket theorem in textbooks? No, but you probably see, but that's a kind of nonsense theorem that you don't have to prove, because we always define the languages at a higher level of abstraction. Or another nonsense theorem is that conversion preserves typing. No, but that you see in every textbook, but you don't have to care in this setting because we only have well-typed. So our equations are between things in the same time. So when we write down the equations, it made sure. And then, so actually, the SOGAT is one level higher than the highest thing that I wrote here, because it makes sure that all of your operations preserve substitution. So that's the extra feature that you get from defining things as a SOGAT. Yeah, but when you want to play with these and prove things, then it's really, so you define it like this, but already in your head you have to think about this. when you prove things, and yeah. Okay. Okay, so what is the general translation? So now we looked at an example, and let's see how this goes on generically. So first of all, here I use some implicit things which were not present when I wrote down here. Yeah.
Yes, I don't think I quite understood the conclusion of this thing that you, because you said, okay, if you write it with the SOGAT, then there, you can automatically, some things become automatic.
Yeah.
You don't have to, but then you also said that you did acknowledge that writing it in the first place in the SOGAT version is more difficult than, like for example, the first things that you wrote before you started doing all the derivations. Or no? Because like things are more high.
You mean these?
So like okay, so you were trying to prove that the application of the right, like IDF.
IDF applied to A is the
Yes.
same as A.
So
Yeah.
for example, so for example, let's say we want to write something like this in the GAT version, right?
So this is the GAT version.
Yes, yes. So we have to always be careful with all this, like the weakenings and everything.
Yeah, yeah.
Right. Okay. So this I understand, but to just express things, like for example, with like each of these parts, to express it in the SOGAT version, is it not more difficult?
To
Like,
express what? The SOGAT version?
So for example, just the thing that you want, okay, the IDF epsilon applied to A.
Yeah, so in the SOGAT version, it just looks like this. So, right, IDF was lambda x dot x, right? So here we just gave a function instead of saying that it's the zero de Bruijn index with an appropriate environment where there is indeed a zero de Bruijn index. And then here, I didn't have to weaken the IDF, even though we know that it doesn't refer to any free variable. So that was taken care of the context. So we had the definition, right, lambda x dot x applied to A. We didn't care about substitution rule, and we just used, and also not about this rule, and I used the beta rule directly to get lambda x dot x A, right? And this, the next step, this one is also invisible because it's done for me by the system. If you like run programs by hand, then this is a step. Yeah. But also, I mean, there are those people who don't believe in this higher level order stuff, or then they just, in their head, they already translate this to this. So actually, in which language you're working, it's, I mean, if you're really, maybe if you're very philosophical, you can think about this, that this doesn't really make sense. This is the only thing which makes sense. And even this doesn't make sense, only the 0 and 1s make sense, which are in the computer, and that's the real thing. But, yeah.
Yes,
So,
yes, the upper thing doesn't make sense for me. This is why I'm confused, and I say that that is more complicated.
oh, so you say that this doesn't make sense?
Yeah, so I always think about the thing on the low.
Yeah. So it was this. So when I learned type theory, I always saw these kind of things in Agda, and I didn't. The first time I thought I understand what Agda is doing was after I learned about CWFs. But I think this is a mentality thing, like how you think or something. I had no idea what these, but I understood Haskell without CWF, but I couldn't understand Agda without CWF. Even though when formalized, they are very similar things. When you write them down as a God. Yeah. Okay, so let's analyze what we did more generically, so that you see how the exact same thing for other SOGATs, like first order logic and whatever, because all of them can be translated to this kind of stuff. So what we did is you always start with a category with a terminal object. Okay, terminal object, which is this thing here. Okay, so whatever your signature is, it's always category with terminal object. And then you go through, let's look at the sorts. So if you have a closed sort like this, then it becomes, well, the real name is pre-sheaf. So it becomes a pre-sheaf on this category. It's or also in categorical language, if we call this category C, it becomes a C of audio set one. Okay, but what does that mean? We just unfold it here, and actually I didn't unfold it here because I was cheating, because I said that, well, I already see that types won't appear there. I looked ahead, but if you implement this in your computer, you might not have a means to look ahead, or maybe you want to do it in a modular way that people can introduce new operations at the end. So then you have to be as general as possible. So actually, what happens to type, or what should have happened to type, is that I should have written the following. So let's fix this now. So for type, I should have written, instead of this, I have to write that types can also contain variables. Okay, so type can also depend on the context. Okay, which means that we also need a substitution operation for types, which has exactly the same shape. So if there's a type in gamma and a substitution into gamma, I get a type in the domain of the substitution, and this also needs to be compatible with composition and identity. Okay, I don't write it down. Okay. So this is what is called a pre-sheaf. Okay, so it's just a family indexed by context together with a substitution operation, which is functorial or which is compatible with this composition and identity. Okay. Then if I have a dependent sort, okay, so it's a sort which already depends on something. It's also just a pre-sheaf. It's just a dependent version of it. Okay, so what is a dependent version of a pre-sheaf? Where it doesn't only depends on context, but also on the stuff that it depended on here. So here was type, here it also depends on type. Now that I fix my types, this doesn't make sense anymore, right? Because type also needs a gamma argument. So actually this becomes really a dependent thing. So what I get is that gamma is a text, then I have a type gamma, and then I get the set. Okay, and let's just fix substitution as well. No, substitution is good, no? Does this make sense now? There is some issue, because I said that a term is in a context and it's indexed by a type in the same context. So if this A is in gamma, then A cannot be in that as well. Okay, and this makes sense that if you think about this, you have a term. You substitute its free variables, that might change its type, no? So, for example, there's a free variable which tells you the length of the vector, and this term has a type vector of some length n. If you substitute that n into the term, then it will also change its type. Okay, so I just have to substitute this type in the end with the small gamma, which is this one. Okay, so the substitution itself becomes a dependent operation. So this is not really a functor; it's a dependent functor. But these are the same. These laws are the same. It's just that these laws only make sense because of these laws. And this is a phenomenon in generalized algebraic theories that I think we haven't seen before in previous theories, that later equations only make sense because you have some previous equations. So this doesn't happen in ordinary algebra, but you need generalized algebra. Okay? And then because of the same reason, I need to fix the comma and stuff. So let's just see. So here, this also needs to be a substituted type. Okay? So I fix the comma operation. P is fine, but Q is not fine. Okay? Because A is in context gamma, but this A is now not in context gamma, but in gamma triangle A. So this has to be weaker. Okay, so which is not very unnatural that in the type of Q, P appears. Okay, the equations are still the same, but again, some equations are only make sense because of some previous ones. So this becomes a, on the blackboard, it's okay, but if you, and that's all the fixes that we have.
That's the context section.
Sorry?
The context extension.
Oh yeah, and we didn't fix context extension, yeah, right? Yeah, so this is a type in gamma, and that type needs to be this guy. Okay, but sorry, so how did I know that I need the, so I said that closed source become sheaves, dependent or open source indexed by other things become dependent sheaves, so this is a dependent sheaf, okay? This is called a sheaf dependent on, right? Okay, so it's like a same kind of shape, but everything depends on time, okay? And then what you need to do is that whenever you have, now we look ahead again, whenever we see that there are some terms on the left-hand side of an arrow, we need to introduce a context extension. And then the category theory people call this thing, what I wrote here, it says that what all of this term is locally represented. That's the technical term, but it just means that there is context extension for it, okay? And then the short way to say what context extension is that we have this triangle operator together with this isomorphism that I wrote here before, that these things are the same as these two things together. And that's what this P and Q expresses in a nice, concise way. So we, okay. And so to illustrate this, we should look at another language which has multiple okay, right? So how did we know that I doesn't need a context extension operation? Okay, actually we didn't know. So if that was also an optimization that I didn't say that TIE also has a context extension operation. Okay, so let's add the context extension operation for TIE to see what we really get. But because no one prevents me here from later introducing an operation like the one system F, like the for all operation, which looks like this. Right? If you have an operation like this, then you need to make sense of this operation. Now you don't only need to collect the term variables by the type variables as well. Okay, so I just erase this. Okay, yeah. So what does the context extension for types look like? We also call it triangle. I mean, now we should call this maybe triangle TM, right? TM there, and we write triangle type. Okay, to know that now this is another context extension operation which extend the context with the type. Okay, so just as for terms, the information that I need to write here is not type, because I don't extend context with type, I extend context with the type variable. So I need to put here the information that I need to be able to declare a type variable, but there's no information here, right? For TM, the A was written after this, so I had to register what the A was, but here there's not. So actually, maybe let's just make it U now. Okay, it's just this. It's just con arrow con. Okay, and then I need all of these operations as well for types. So the short way to say it is, as we discussed, is this thing. So a substitution from delta to gamma extended with a type is the same as a substitution from delta to gamma together with the type in delta. Okay, and this direction is called comma type. Okay, that's the comma operation, the same as this one. But now I don't extend the substitution with a term, but I extend the substitution with a type, and then I get something like this. Okay, and then this direction is encoded by p tie, actually post-composition with tie, right? Because we want to go from here to sub delta gamma, you have to post-compose this substitution with the P operation for tie, right? The P operation tie is this sub gamma triangle tie to gamma, right? And then when I want to go from here to here, I just substitute Q tie by this. So the Q tie operation is a term, sorry, it's a tie in this context, right? So these are the new stuff. And then they form an isomorphism. And then, so, or, I mean, you could write them down line by line, but this is the more concise thing. And now what is a context? So now context is not a list of types anymore, right? It's a list of types, and anywhere in the context there can be marks which just mark the presence of a type variable. So let's look at an example of context. So empty. Maybe I extend it with a type variable. Okay.
Can you maybe grab a white font?
Oh. Oh yeah. I just switched into the new blue mode. Yes. Okay. So maybe I extend the context with a type. Then I extend the context with a term, which I need to give its type. Okay. Then I extend it with another type, and then another term, and so on. Okay. So this context has actually 1, 2, 3, 4, 5 variables, right? And the 0 de Broglie index here gives, in this context, gives something of type B. The 1 de Broglie index gives a type. Yeah. In this context, there's no, it's not that we have 0, 1, 2, 3, all 4 terms and all 4 types. Now we only have very certain, so, right, because this 0 is a Q term, okay, while this one is a Q tie weakened by a P term, because here we forgot a P term, okay. What is 2? Oh, 2 is also a tie, so it's a Q tie, which I first weaken by a P tie, and then I weaken by a P term, okay. So now, basically, the variables are the way it's well-typed in this. This is, and they are decorated with a list of. It's decorated with a binary number, right? And not all of them make sense. Only those make sense which are adding extra dependencies, types, and terms exactly as they are in the context. So it's a much more subtle structure. And you can imagine there are theories where you have. What's the simplest theory where you have 3 different kind of variables? I didn't list any of those. I mean, in first order logic, you have 2 variables, term and 2 variables. In system F, you also have type and term. In system F, oh my God, there's also only types and term. There are no kind variables, right?
Second order logic.
Sorry, what?
Second order logic.
Oh, second order logic. Yes, yes. So where you have terms, then you should have propositions as well, and yeah, you can quantify over subsets, yeah, of terms. Yes, terms and subsets of terms, propositions on terms, and proofs as well. Yeah, yeah. Okay. Okay, so so this is how you translate. But if you don't know what will happen, you always need to have context extension for all of your sorts. Or you have some language of SOGATs where you have some mark, you somehow need to mark that this is a set plus, and that means that we have variables for those, but not for this. And then this arrow is actually not a real arrow, it's an arrow plus. Okay? Because you can only put on the left-hand side of something which is in set plus and not in set, or something like this. You can restrict. Okay. So, right, and then what happens? So we discussed what happens to the operations. They become presheaves and dependent presheaves, which might have this context extension stuff after this category. Okay, so what happens to operations like this? Well, the operations just get decorated with gammas, right? So here's the operation. We just put a gamma everywhere, right? Digamma, 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 and then we need to have a substitution rule for all of them. So the categorical way to say this is because the operation become natural transformations or dependent natural transformations. And this naturality is that they behave nicely with instantiation, or that there's defined substitution rule. But it's quite clear what you need to write. So it's like you can just run the algorithm, but you can do it by hand, because what else would you write here? If you have an A arrow B and you want to substitute it by gamma, then it just goes under the type former arrow. Okay, and then the same for all the other operations. Okay, but that's not enough, because when you this is the same for arrow and the dot. So what happens if you have binders? Now these are interesting. So the arrow pluses, so the arrows which are inside an argument, the left-hand sides of the arrow, they just become context extension. Okay, like here. From this arrow, this is the arrow plus, we got a context extension. Let's just look at another example where, like, for example, the case operation for, no, not the case is not good. The iteration principle for product type. That's interesting because it's a binder which binds two variables, right? So if you have product type, you have times, tie to tie to tie. And then you have some induction, let's do non-dependent iteration for this. So how do you do this? So if you have a C is a tie, and then you have a TMA or TMB, TMC, then you can go from TMA times B to TMC, right? This is what Frederick wrote down yesterday. This is what his system generates automatically. And now this is second order because there are these two things here. So what does this look in the first order representation? So this argument is some gamma. It has type C. But what is the context? There are two arrows here. So I have to extend the context with the A and the B variable. Okay. So this is translated to this. Then I get a Tm gamma A times B. And then I get a Tm gamma C. Okay, and we're not done because we also need the substitution rule. So this becomes this thing together with its substitution rule. It says that if I apply eta to some W when AB, okay, then I substitute with gamma. It's the same as eta, where the W has to be somehow substituted, and I also substitute the AB with gamma. So how do I substitute the W? Okay, so with the law, we had to do this up arrow, this lifting, this compose P, Q, and now we just need to do it twice. Okay, so the gamma substitution goes into gamma, but now I have two extra stuff. And again, in the delta, I will have two extra stuff. So what I need to write here is a sub from delta, which is extended by AB, to gamma, which is extended by A and B. And so it's gamma compose P, Q, compose P, Q again. Maybe you can write it that way, but you can actually merge this and make it into one list. If you want to check this, look at the exercises in the course notes. And maybe there is one more subtlety that actually, if types are now indexed by context, then this also doesn't make sense. Because here the A is in delta and here the A is in gamma. Okay. So the real type of this is that this A has to be substituted by gamma. Okay. Because A is in gamma, that's clear, we accept that. And then if I substitute A with the small gamma, which goes from delta, then this makes sense. Okay, so the question is, what do I need to substitute B with? Makes sense of this. I mean, it can't be gamma, because gamma only gives me the, so what is the type of B? Right? B is a type gamma triangulate, right? And the small gamma only gives me the gamma, right? So it is just gamma, right? So this kind of liftings already appear in the type of the bigger liftings. The smaller lifting appear in the bigger lifting and so on. Okay. Right. So the time is up. So okay. So today I showed how to translate SOGATs into GATs, and maybe now you have enough. You've seen enough examples that now you can translate any SOGAT into a GAT, and then you can just use these GATs now if you want to prove something about your GAT. But actually, there are people have worked quite hard on this and developed techniques to prove things for SOGATs directly, because when you prove something for this one, you need to give all these components, which are basically twice as much as this, right? When we give so it's really annoying that you need to write down all these things and check all the substitution rules and stuff. So, but now we have some techniques with which you can just so we have alternative induction principles which use the original induction principle for the big GAT, but give you an interface where it's enough to give as many components as the ones in the SOGAT and achieve the same thing. So, for example, canonicity and normalization proof for type theory or simply type lambda calculus can be factored through these more general induction principles, so that when you do canonicity, you only need to give as many argument operations as this. So in the course notes, I explained how to do this for canonicity, and I will hopefully also add it for normalization, but that's a bit more technical. So I haven't added yet, but you can already read and completely understand because you know everything what is needed for it. So there I showed you what is the kind of I call it second order dependent model. So second order dependent model has as many components as the SOGAT, and it's a second order kind of thing. So it contains some second order functions, and I showed how to compute a first order dependent model from the second order dependent model, which you can directly apply to the syntax of this thing. Yeah. Okay, and also you look for the course notes for more pointers on this stuff. So these things I did in so you know you can discuss type theory very syntactically or very semantically. So so I had these levels of abstractions in the beginning, but this is a different axis. Actually, in this different axis, basically all of them are in the very high level of abstraction, and even there you have lots of choices. So maybe just the very semantic is locally Cartesian closed categories or path categories or something like that, while the very syntactic one is like extrinsic description, and then you have things like contextual categories, and you have CWFs, and you have James Chapman style inductive type intrinsic description of type theory, and there's this whole scale, and we just did it here with CWFs, or maybe you could also call this the QIIT approach with QIITs, but there are all these other different approaches, and yeah, so you can. So a lot like if you go to a homotopy type theory conference, everyone will do some very semantic thing, very categorical thing. If you go somewhere, like if you go to Nantes, then everyone will do something like this, or talk to Theo, or yeah. So this was the one I explained here. Yeah. Okay, that's it. And it's lunchtime, right?